So we've already seen examples from this data here in example one, where the population, where a sample mean is taken, and then a different sample mean is taken, and we've gotten different values. So already we have seen that maybe sometimes we're getting, if this is say 20 and this is say 21, we've seen data that gave us a number that was very close to 21. We've seen data that's given us a number that was a little bit lower than 21. So the probability that it's exactly either one of those numbers is rather low. It is more likely that it is maybe somewhere in between some of those numbers. So the probability that it's exactly is basically zero. So instead of using just one value, like a point estimate, to estimate the population mean, instead we're going to use two values. And those two values are going to be the endpoint of some confidence interval. Or better, more generally, it's going to be the endpoints of some interval estimate. So instead of just using one value to estimate the parameter, we're using two values and saying that it's between there. We're saying a range of values, which we can do with continuous variables. So essentially, we have some point estimate in the middle. We're moving to the right, we're moving to the left to form this interval. And how far to the right or how far to the left we move is our margin of error. And before I can calculate how far right or left we're going, we need to determine how confident we want to be with this estimate. How confident we want to be that the interval estimate will actually hold the population mean mu, so that the true mean will be somewhere in that interval. 90% confident, 95% confident, so on or so forth. And however confident we choose or are told to be is our confidence level. I want to take a second to talk about what that means exactly, because what it means is important because it will determine how we interpret our confidence intervals. Remember, a big part of this course is not just being able to calculate these things, but being able to tell me what these things mean. So the confidence level is the probability that the interval estimate, remember, the interval estimate is just some interval that we're using to estimate the parameter, contains whatever it is we are trying to estimate, assuming that this estimation is happening a whole bunch of times. So the more times you do it over and over and over, you can then say with 90% confidence that the population mean will lie between certain two numbers. So the level of confidence, whatever level of confidence you have, that determines your critical values. What critical values are is they are values on the bell curve that separate usual data from unusual data, probable data from improbable data. So critical values are the values that separate sample statistics that are usual from sample statistics that are improbable, not very likely to happen, or unusual. And we saw examples, we didn't call them critical values, but we have definitely seen like cutoff points in the bell curve where we talked about people that were percentages of people that were taller than Shaquille O'Neal, or what percentage of people were shorter than Kevin Hart. Same idea there, that we're dealing with this usual and this unusual data. So for instance here, say you had chosen a 90% level of confidence. You want to have 90% of your data in your bell curve. These two numbers down here, those two Z sub C's, would be your critical values. You have two of them. You have one for the upper value and one for the lower value. They are the same number but with opposite signs, because you move the same distance to the right and the same distance to the left when we're going to be forming our margins of error. Okay. So, and typically, and all the even though we do have two critical values, in all the formulas that we use, we will always use the positive version of the critical value. We will not be using the negative version of the critical value. Okay, so let's look at this here. So here's an example. This area on the inside is 0.9. because I want to be 90% confident. So to figure out what those critical values are, I know that if the area in blue is 0.9, then the area that is shared between those two tails is 0.1. That is shared in the left tail and in the right tail. So if 0.1 is, and I got that 0.1 by doing 1 minus the 0.9. That's where this 1 minus c is coming from. If that is what is shared in those tails, then to figure out what is in just one of those tails, I need to divide this 0.1 by 2 to get 0.05. So I now know the left area of that negative critical value. I know the left area of that negative critical value is 0.05. So I'll mosey on over to my standard normal table, and I'm looking for the closest value to 0.05. I see 0.0495 and 0.05, so I'm going to take this negative 1.64 and 1.64 and the negative 1.65 and average them together to get negative 1.645. That's what the left critical value would be, the negative one. So the other one is the positive 1.645. They're the same value, but with different numbers. So same thing, they found the area in one of the tails off to the left. You look that up in the standard normal table. You could have also used a calculator or StatCrunch. We have seen many examples of how to find these z-scores once we know the left area of them. And then the other critical value is simply the positive one. So I want you all to take a second and do the same thing to find the critical values. Well, what if you have a 95% confidence level? So that graph would look different, because if you have a 95% confidence level, that means that in your bell curve, between your two critical values, you have 95% of the data. You need to then figure out, well, how much data do you have shared in both tails? And then you need to take half of the shared data to see, well, how much data is just in one tail. And once you know how much is in one tail, you can then go find this negative critical value, because it should be having that as a left area. Okay, and if you were to do that, in fact, my screenshot is not complete, but the standard normal table actually does include different critical values for very common very common confidence levels. So keep that in mind. So now that we know how to find critical values, there's a few more definitions we need. The sampling error is the difference between the point estimate and the actual population parameter. So again, another example, the same thing that I talked about in the introduction video. They use 63.5 for the estimate of the average height of women. Let's say that it was actually 63.21. So what the sampling error would then be, it would be the difference between those two numbers, the distance between those two numbers, how far we actually were off. So that blue, that's really thick, that blue distance there, that would be our sampling error. Tells us how much of an error our sample had, and I would have gotten that by 63.5 minus 63.21, which would have given me 0.29. If 63.21 was the actual mean. So generally, we will not be finding sampling errors. We're not going to spend a lot of time finding them, but I did want to give you that definition. And the reason that we won't find a lot of them is because, remember, the whole purpose of this lesson is that, for the most part, population averages are not known. They're usually always estimated with really good samples, because it's so difficult and so expensive to get population data. And another reason why we won't be using that is because, let's say if I had chose a different sample of women, maybe my point estimate would not have been 63.5. That 63.5, I bet you the average height of women will be different next year, depending on the new data that's collected and then compiled like that. So that's another reason why we won't typically be talking about the sampling error, because even the sample mean will be changing from sample to sample. But what we will be talking about is the margin of error. And the margin of error is the greatest possible distance between the point estimate and what the actual value of the parameter is. And that's what we're interested in. Just how far out can we go and still capture the mean? So the formula for the margin of error, specifically, this formula is very specific to these conditions. It is specific to the conditions that you want the population mean mu when you know the population standard deviation sigma. That's the only time you can use this formula. E is equal to Z sub C, your critical value, multiplied by sigma, your population standard deviation, and then divided by the square root of n. You may also notice that this sigma divided by the square root of n part, that hopefully looks familiar because that is sigma sub x bar from when we used the central limit theorem. Because the central limit theorem is what told us that these different sample means are normally distributed, which is exactly what we are working with. Because remember, we just said the sample mean is going to be changing from sample to sample. We can use this formula for E, and we will be checking these conditions when the sample is number one, random. We do need to have a random sample in order for this to be accurate. And one of the following conditions has to be true. Either the population has to be normally distributed, or n has to be greater than or equal to 30. The sample had to be greater than or equal to 30. And hopefully those conditions look familiar too, because those are the same conditions from the central limit theorem, which is exactly the kind of problems that we're working with. The central limit theorem told us probabilities that a mean was greater than a certain value or less than a certain value. So we're now finding the probability that a mean is between two values. That's what we're doing with these confidence intervals. And in order for us to do that, we do need the central limit theorem.